Okay, you've just submitted your last homework assignment for the semester. That's got to feel good, right? Except for that knowing that there's an exam coming up. That makes it feel maybe a little bit less of a relief. But the exam will be over soon enough. Actually, a week from today, some of you already finished with it because we'll have 2 hours. It'll go from 8 to 10. It's a comprehensive exam, meaning that there can be questions from at any point in the semester, but there will be added emphasis on the material that we've covered since the second exam. So that means that the questions from exam 2 until now would probably be more in-depth in a technical nature, where questions from the beginning of the semester would be more overview type questions rather than detailed calculations. There most certainly will be questions where you'll need to use a computer, so you'll have access to the tablets if you're feeling like a gambler, or you can bring your own computer if you want a sure thing. The exam's comprehensive, so it could be anything. So yeah, including WMS. Yeah. Yes, there will be 2 parts. There will be both conceptual questions and problem solving / computer questions. And so on the conceptual questions, I'd encourage you to review the concept inventory handout that I gave you at the beginning of the semester, and that lists the key terms associated with each chapter in the book. You can bring a 1-page equation sheet for use on the problem solving / computer portion of the exam. You can't use that during the conceptual questions, though. We'll talk a little bit more about the exam in class on Thursday. We're going to switch gears a little bit and start talking about groundwater today, Chapter 6. And groundwater hydrology is a topic, unfortunately, we've just got 2 lectures for, but it's the sort of thing that someone can go earn a PhD on just a part of groundwater hydrology. It's an enormous subject with lots of courses that focus on the movement of water underground. And that's important for a lot of reasons. It's important because, unfortunately, a lot of our underground water is contaminated from industrial sites in the past that were a little bit sloppy in how they handled waste. And so now there's gasoline underwater, there's dry cleaning fluids underwater, all sorts of nasty things under there that you don't want in your body, and yet so many communities rely on groundwater. And so it's really important to understand how the water moves around for quality reasons, and also just because a lot of places, even when the water is pure, rely on groundwater for irrigation, and they're pumping out more than can be recharged over time. And so there are really sophisticated models similar to WMS that map the underground environment. So in the same way that you would put together a coverage that characterizes the soil type and the land use for a surface, there is underground data that says what soil types there are at certain depths. And so they'll create, rather than a surface, they'll actually create sort of a 3D underground environment and then apply equations like Darcy's law to say for certain certain elements of soil how the liquid can move through there over time. So just to give you an idea of where the water is on Earth, by far the majority of the H2O on our planet is in the ocean, 97% of it. And that's not usable to us without a lot of effort. In order to make seawater usable, you have to distill it with thermal distillation, which is very energy intensive, or membrane distillation, which still uses a lot of electricity, but less than thermal distillation. But then there's some equipment issues, really easily fouled membranes and high setup costs. So ocean water is not really usable. If you look at what's next on the list, ice caps and glaciers aren't very convenient either. You don't hear about people dragging icebergs from the South Pole up to cities and using that for fresh water, although it's been proposed as novelties. Like there are a few vodka companies who want to make their products out of icebergs, and just for the novelty of it. But the most The greatest quantity of fresh water that is easily available is groundwater that's less than 1 kilometer underground. That's the depth at which the average farmer can put together a pump and extract water from underground. And although it's only 0.3% of the water that's available, that still accounts for a huge quantity. So let's watch a couple of videos that talk a bit about groundwater and how it's used in the United States. By the way, did anybody watch the video for the last lecture? The audio's totally screwed up for like the second half, and I was trying to figure out why that is. It's because of once I started the demo, the floodwater calculator thing? I left it running in the background, and it has like the sound of water running, and so it recorded both my microphone and the system audio. So I'm not going to make that mistake again.
In the state of Kansas, agriculture is king. Along with high yields of corn and soybeans, Kansas is the top wheat-producing state in the U.S., with yields of more than 382 million bushels in 2012, according to the USDA. The secret to this land's bounty is not just the soil that covers it, but also something below ground that no one can see: the Ogallala Aquifer, the largest freshwater aquifer in North America.
For decades, you've had incredible production of agricultural crops on top of this, and largely that's because of the incredible water resources that have been available to it.
The Ogallala Aquifer, also known as the High Plains Aquifer, is a groundwater storage reservoir that stretches 174,000 square miles underneath parts of 8 states, from South Dakota to Texas.
This well here is 303 foot deep.
Stan Townsend, a 6th-generation farmer from Weston, Kansas, grows corn, wheat, pinto beans, and peas on his land. Like many farmers, Townsend depends on the aquifer to irrigate his crops, especially during times of extreme drought.
This country is about weather, and right now it's sure not in our favor.
Today's irrigation technology is able to pump out water that has been in the aquifer for hundreds of thousands of years in just a matter of minutes, a rate which far outpaces how fast nature can replenish it, threatening the overall sustainability of the aquifer and agriculture.
This well over on the southwest was right at a 2,000 gallon minute well, and now all we're getting out is about 600.
According to the Kansas Geological Survey, groundwater levels in the aquifer have dropped an average of 14 feet since 1996, about a foot a year. Aquifer drop rates suddenly doubled, an average of 2 feet a year between the start of 2011 and the end of 2012 alone.
Since about 2011, there's been a significant drought, and this is really across most of the High Plains Aquifer, but this area, as well as others, you're now in a period of extreme to exceptional drought.
Dave Heineman, a hydrologist at Michigan State University, is leading a team of scientists funded by the National Science Foundation that is studying the aquifer. The team is analyzing data from as far back as the 1800s on changes in climate, irrigation technology, and water policy to build models that could forecast what the future holds for the aquifer and for farming.
But when we feed the climate into these models, we're able to predict what happens with the water levels. And as long as we have pumping data, we really get a great understanding of the system.
One of the reasons why the aquifer replenishes or recharges so slowly is due to the water cycle itself. When precipitation in the form of rain or snow hits the ground, some of it runs off. Some evaporates back into the air from the ground, or is transpiration from plants. What doesn't run off or evaporate slowly seeps down through the soil and its layers by gravity in a process called percolation. In western Kansas, it can take 1 year to recharge the aquifer by less than an inch.
There's not enough recharge out here, not enough precipitation.
During the drought of 2012, Mitchell Ballman, a 4th-generation farmer outside of Hoxie, Kansas, was able to maintain his crop yields only by pumping more water out of the aquifer.
In 2012, we were drastically impacted. I mean, it affected our crops, definitely affected the aquifer. We depend heavily on the Ogallala, which is what we're pumping up for our pivot irrigation.
Now, in an effort to extend the life of the aquifer, Ballman and other farmers have started a grassroots effort to cut back pumping by 20% over the next 5 years.
I think we're averaging probably 2.1 foot a year is what we're dropping. That's why we're looking ahead to the future to try to promote saving, being proactive instead of reactive.
But sustaining the Ogallala aquifer and Kansas agriculture must also include more scientific research. Hyman's team is working with local and state government officials, water policy experts, and farmers to develop a long-term model for aquifer water use, based on more precise measurements of precipitation, percolation, and natural recharge, better monitoring of agricultural pumping, and forecasts of changes in climate and population.
To do anything about sort of forecasting what happens in the future, we have to work with both the farmers and the policymakers, because as we do these scenarios of the future, we have to have a pretty good idea that the scenarios we're running are feasible.
We've got to start someplace. We've got to get this thing moving. It's still important.
Improving water policy and reducing water usage are not only key to sustaining the Ogallala aquifer, but also to maintaining a way of life in western Kansas and across the entire High Plains region.
So, let's draw a little cross-section on the board of the aquifer and what's happening using a mass balance idea. We've got the surface, we've got the underground environment, and here's the water table, and then at the very bottom is a layer of bedrock. All right, so here's the surface. We can do a control volume, and inside the control volume is the surface and the air above it. Here's the land surface, water table, and bedrock. So, what's the main point of the video? The water table's going down. They said 2.1 feet per year. Now, the depth of the aquifer varies from place to place, and I don't know what the average depth is, but they seemed worried about it enough to where, farmers themselves are talking about the need to reduce irrigation. Usually, farmers are not the most proactive in acknowledging environmental issues like this. So it must be pretty critical. Why is the water table dropping like this? What's that? They're taking out more than is getting in. Right. Very good. So there's a well, and let's draw a well to the very bottom. And there's these little screens on here. Sometimes, the drawing symbology is important because it tells you a story. There's a shaft that penetrates all the way down to the bedrock, and there's these little slots in the pipe. It's called a screen. And the reason for the screen is you want water to be able to seep into the well casing, but you want to keep the soil and the rocks out. It's not to keep the water clear. Actually, the water is clear. You'd think that water touching dirt would maybe be muddy or something, but it's not. The water that flows through the aquifer is crystal clear. The soil itself is acting as a filter, but the slots in the drain is just to keep the soil on the outside of the well. So the main problem is that they're pumping out a lot of water, and it's more than is percolating. Now, actually, two different people put it two different ways during the video. One person says it's not raining enough, and another person said there isn't enough infiltration or percolation. And so it was actually showing, there was a little animation that shows that there's rainfall, which of course some of it leads to runoff, and it showed that there was, I need another color, I got red, yeah. It showed that there's evaporation, so of course evaporation is squiggly lines. Evaporation, and then some of the water does percolate downward. And what were they saying? That in some cases there's only 1 inch of infiltration in a year. And so, you know, the rainfall in maybe central Kansas is probably on the order of around 25 inches per year. And so of the 25 inches of rainfall, only 1 inch is percolating, and the rest of it is either evaporating or evapotranspirating. Evapotranspiration includes the water that gets into the plants and then is released through the plants. That's transpiration. And then, of course, there's runoff. And there are a lot of rivers in Kansas, some really large ones. And so a big fraction of the water is running off. So what's the solution to this? You know, there's maybe not just one solution. Maybe there's lots of little things that could be done. Yeah? Uh-huh. Okay.
Taking all the water and putting it in retention ponds, I believe, some of the pond. And I think the chief factor got, the company was from California and brought Texas just to be there because of the water. It was only used for farming.
Okay, so you're saying instead of pumping from the aquifer, find alternate sources of irrigation? Okay, good. Alternate water sources. And so, you know, the water from milk in the UAE, where I've spent some time, they purify sewage and use that for irrigation. There's actually 2 parallel water networks, one for drinking and the other only for irrigation. And the irrigation water literally comes from the wastewater treatment plant. And so that goes into alternate water sources. What else could be used to help overcome this problem of the water table dropping 2.1 feet per year? Promote infiltration. Very good. How do you do that? Okay, good. Ponds. So that could be ponds. You know, like if they amend the soil to try and enhance the water to get in, that would help. And of course, the other thing that's nice about a pond compared to just having it at the surface is that, you know, if you've got a pond like this depth of the water causes a pressure, a hydraulic pressure that's forcing the water down into the soil more than if it's just a very shallow puddle. There isn't as much of a driving force to overcome if the soil is saturated and it's not necessarily hungry for the water, then having that tall column of water can help promote infiltration. Okay, so increase precipitation. Now this is one that's a little bit controversial, but I mean there is evidence that you can enhance infiltration by cloud seeding, and sometimes they'll use silver particles. I'm not sure, I haven't looked into it enough to understand why it's silver that's so frequently used for cloud seeding, but the idea is that sometimes the humidity is there in the atmosphere, but remember, if we talk about what causes precipitation, there has to be some sort of lifting, because it's the lifting process that takes warm, moist air at the surface, taking it upwards makes it cool, and then as it cools, the relative humidity increases, but it can't precipitate unless there's some sort of a nucleus for that humidity to condense onto. And so cloud seeding is the idea that if you're flying around in an airplane and shoveling silver particles out the door, then those silver particles are going to act as a nucleation site for the humidity to condense onto, and then it can precipitate. So, yeah, thinking in terms of the mass balance, you know, where we want the water table to go up, so there has to be more percolation. So one of the ways to get more percolation is to increase rainfall. So look at the mass balance. Remember, mass balance is accumulation is the difference between in and out. Right now, out is bigger than in, and that's why accumulation is negative. That's why the water level is going down, is because we're pumping out of the system more than the inflows into the system.
What about like, I guess it's like farmland and stuff like that. The ways that farmers plow their fields to slow the runoff?
Yeah? Okay. So, I don't know how we'd put that. There's soil conservation. Sometimes they talk about like soil conservation to promote infiltration. One thing I've heard is that you see some farmers will like totally plow under their fields every year, and some farmers will just plant without totally turning the soil over. And when you do the latter, when you don't totally turn the soil over, actually there's less evaporation. The soil loses less of its moisture, and there's less loss of minerals. And so some people will just plant right with like the leftover corn stalks from the previous year in the same way. All right, so that's to try and make more in. We've talked about more rainfall, trying to enhance percolation.
Could you design better crops that require less water?
Yeah, absolutely. Crops that use less water. Now, not so much in Kansas, but another place where they're having a huge drought right now is California. And one of the crops in California that uses the most water is rice. Rice is very water intensive. And really the only reason they've been growing rice in California is that, you know, for the last 50 to 100 years there's been plenty of water coming out of the mountains of Northern California to where they could do this ridiculous thing of growing rice in the desert. They could, you know, they redirected the water from the mountains to the desert and were able to grow rice. So the farmers love to grow rice just because they've got the equipment for it, they've got the expertise, but sometimes you have to change your thinking a little bit. Are there crops that demand less water? Are there things that are more suitable for the natural environment? And so in Kansas, not every crop has the same embodied water demand. You know, a kilogram of wheat, to produce that kilogram of wheat probably requires a different amount of water than is required to grow a kilogram of pinto beans. And I don't know the difference between those crops, but the farmers probably do. And as water becomes more expensive, because the lower the water gets, as the water table gets deeper and deeper, it takes more electricity to pump it out. And so that water costs more for the farmer. They don't have to pay anybody for the water, but they do have to pay to pump it out of the ground. And so the water, the real cost of that water is getting year by year more expensive for them. And so they're having to think in terms of, well, I can maybe grow more corn, but the pinto beans requires less water. So there's going to be a natural crossover at some point that forces them to examine the water demands of different crops.
Could they build like storage tanks?
Okay.
Kind of like the ones that they go underneath our plants instead of just collecting water?
Like rainwater storage tanks? Yeah. It would be really tough to collect enough for them to use in appreciable quantities. But along those same lines, sometimes the underground environment is adjusted to enhance recharge. And let me show you another video of something that's taking off in India. It's the opposite of a well. You know, a well is a hole in the ground where you're trying to take water out. This is a hole in the ground where you're trying to put water in. And so in doing this, if you think about it, you know, what's the cross-sectional area of that well? You know, like maybe 1 square foot of area. You can't get very much recharge in 1 square foot of area. But then drill a hole down, and what's the surface area of that well casing with the soil underground? So what they've done is they've basically I'll draw it in a minute. But you see this really large field full of water. There will be a little bit of infiltration underneath that ponding itself, but by redirecting that water underground, they're able to really increase the total amount of water that gets into the soil versus runoff. Because when it's a big field puddle like that, a big pond, you know, once the storm is over, you're going to be losing a lot of water to evaporation if it's pond for recharge. But if you recharge it through a well, you're not going to be losing it to evaporation in the same way. You know, here we've got our surface, our water table, and rock. Over here, when you start pumping from a well, what happens is the water table actually begins to bend. It bends downward like this in the vicinity of the well. You know, even if you're not pumping out so much, even if the water table is steady, it still goes down a little bit in the vicinity of the well, and that's what causes the migration towards the well casing. It's a natural okay thing for this drawdown as it's called. But over here in the video we just watched, so there's a casing and a hole dug, and instead of pumping out, injecting water, and it causes sort of like the opposite of drawdown, and the water flows outward like this. And so what I was talking about, like the surface area, so you know the surface, at the surface the area of that opening is very small, but now think about the area of the cylinder, the outside area all the way down. If this is slotted like this, now all of a sudden you've got an enormous surface area, and because of the ponding inside of the well casing, you've got a pretty good driving force that's pushing water back into the aquifer. And so this is really efficient also because there's going to be so much less loss due to evaporation. So trying to increase recharge is another one of the ways to improve the in. So, you know, it's a balanced solution really. You want to work with the people who are using the water and say, you know, really, do you need to use as much water as you are using? Are you growing the smart, sustainable crops, or are you growing crops that are only possible because electricity is artificially cheap? You know, the corn, the beans that are being grown, really, those are grown from coal. You know, if you're eating coal when you eat crops that are produced by electricity that's used to pump the water, and the electricity comes from fossil fuel. There's embodied water, and really what underlies it all is embodied energy. And so when you're using more water than can be sustainably removed from the system, then the only way that's possible is through fossil fuels. And so putting the accumulation back into balance is trying to find ways to increase the infiltration and reduce the outflows. Yeah, yeah, but pollution's getting in there anyway, you know, through the surface. I guess it's getting filtered. You know, if you think about, they sometimes call, if there is like a contaminated pond, you know, like a duck pond. You know, ducks are dirty. They have lots of germs in their stomach, and so like here's a duck pond, and if this was going to be used for drinking water, then the water table has to be separated from the duck pond by a certain depth of soil, because the soil will naturally, if the contaminated water is traveling downward, the soil naturally attenuates the bacteria that are in the surface waters. And so I don't remember the exact depth, but usually it's, I don't want to say a specific number, but there is some federal regulation that, you know, drinking water wells have to be a certain distance away from surface water, otherwise they call it that it's under the influence of the surface water. So injecting this, you have to have your withdrawal well, you know, because probably somewhere you've got a well that's for going out. You know, here's your recharge well, you'll have a production well, question is this production well just only going to be used for irrigation, or is it also going to be used for drinking? And if it's just for irrigation, then we don't really care about it being too close to the recharge well. But if it's going to be used for drinking, then you do want to have a certain distance because the soil matrix acts as a filter. So here's some terms that we've got to learn before we can get into calculations. An aquifer is just any sort of a underground formation where water is present. It doesn't have to be soil. It can be fractured rocks. It can be gravel, even clay, although clay transmits water very slowly. Aquiclude is something that has water but can't transmit it. So here, this layer that you see, there's two layers, both on top and on the bottom of the confined aquifer. That is an aquiclude. Clays have a very low hydraulic conductivity, but they're full of water. They're saturated. And the aquafuge, just to distinguish between the aquiclude, is something that doesn't have water and can't transmit it. So a rock, for example. In this drawing, you can see a little schematic of here's a hillside, and if there's rain on top of the hillside, then what that causes to happen is that the water table will be relatively high over here where there's recharge. And because of this confining layer on top, that recharged water is perched higher than over here where the water is being extracted. And that's the cause for this artesian well over here where the water is actually flowing out at the ground surface. You can see that the piezometric pressure is the sum of the pressure divided by gamma plus Z. All that really means, a piezometer, to refresh your memory from fluid mechanics, the piezometer is the idea that if you, at its simplest conceptual basis, if you have a pipe and you put a hole in the pipe, then water is going to spray all over the place. But if you connect a little tube to that pipe, a tall tube, then however much pressure there is inside of the pipe is going to cause the water level to rise to a certain elevation. And so the delta H, how high the water level will rise in a piezometer, delta H is pressure divided by gamma. That's a piezometer. So in these cases, we've drilled a hole into a pressurized underground environment. This pressurized aquifer is pressurized because the recharge area is kind of specially configured. This is a unique case. It's not always, the underground environment isn't always pressurized. Usually, you don't have a confining layer above another confining layer. Artesian wells like this are kind of rare. But you can see that the water level rises to a certain height having to do with how much pressure there is underground. And here it rises to a certain level, but it's not above the ground level. But over here, there's still pressure, and the ground level is lower, and that's why the water is spraying out at location C. So this is illustrating an unconfined aquifer is just where there's a confining layer underneath, but nothing above it. So the water can recharge directly at the surface and go down to the unconfined aquifer. But it gives you an idea of what a confined aquifer is. And we have different equations for both unconfined and confined aquifers when we want to take a look at wells and how much water we can get out of wells. The equations are slightly different. Any questions about this representation? If you had some sort of like a hypothetical exam situation and you were asked to sketch a confined aquifer, would you be able to do that? Sketch a confined aquifer. That's a really good question. All right. I'll probably forget when I'm working on the exam, but that's just to give you a peek into my mind on like what sort of questions I think are good. All right, so an artesian aquifer is what we had illustrated here. Artesian means that there's enough pressure underground that flowing water comes out at the surface when it's penetrated by a well. And I've actually seen an artesian aquifer, a couple of them. Is there? Blackwater Falls? Now, the one I've seen is actually out in the desert in Utah, next to the mountains. Not where you'd expect to see water coming out of the ground, but it does. An aquitard is any sort of a formation that slows down water flow. It can be a thin layer of clay. A leaky aquifer, let's say that under here, you see this confining layer? If this layer wasn't totally full of water, then it would be possible that water would be leaking from the unconfined aquifer into another layer beneath it. And so a leaky aquifer, this one wouldn't be leaky. If anything, the waters may be migrating upward through this confining layer from the pressurized aquifer. But if it was dry underneath the clay layer, then water would be probably leaking through the clay layer from the unconfined aquifer. So that's a leaky aquifer, is when you have a semi-pervious layer. What we have here is, it could be a leaky confined aquifer if this is relatively thin, or if it's semi-pervious, then this unconfined aquifer could be because there was leaking upward, just because of the pressure. So remember Darcy's law. Here we've got this test device oriented horizontally. That's always what makes the most sense to me, is the idea that water is forced to flow through some sort of a soil column, and it's a cylindrically shaped soil column. You can see they're saying there's a cross-sectional area of this cylinder. You could think of it as like a PVC pipe that you packed full of soil. And so your pipe has a certain length L that is known, and it has a certain cross-sectional area that's dependent on the diameter of whatever pipe you selected. And then you connect a reservoir upstream and downstream. And you know how deep is the water upstream and downstream. You have a pool of water that has this H in height on the upstream end, and H out, which is how high the water is on the downstream end, isn't as tall, and so there's delta H, the difference in the height of the water between the in and the out. And so Darcy's law says that there's this mystical parameter, K, the hydraulic conductivity, that relates the flow rate through that cross-sectional area as a function of the difference in the height of the water of the in and the out and the length. And so this is it all fits together so neatly. It doesn't always fit together so neatly as this. If we look at the units, hydraulic conductivity is length per time. So it would be centimeters per day or meters per second, however you want to express length per time. Cross-sectional area is length squared. And so from these units you get length cubed per time, so cubic meters per second, for example. And then this ratio is unitless. Delta H divided by L is a slope. It's the slope of the grade line. You can think of it as the driving force. So connect a line, an imaginary line, from this water surface to that water surface, and delta H divided by L is the slope of the piezometric pressure through that apparatus. Okay, hydraulic conductivity is this K value. You can characterize the K value by extracting some soil in the field, tanking it into the lab, and performing a test like this. Another way we talked about the infiltrometers earlier in the semester. That's another way of getting an idea of infiltration rates. Here's a nice diagram that shows what happens when you pump out of an aquifer. And it shows the cone of depression. I've always liked that phrase, cone of depression. I felt myself in a cone of depression at the end of the semester when I know I don't get to see you guys anymore. It's just, it's so hard to think about all that vacation time we're going to be enjoying soon. So look, there's two different lines here. There's this dashed line, and then it's saying cone of depression for a lesser pumping rate. It's confusing here because we've just been talking about the Ogallala Aquifer. And in the Ogallala Aquifer, there's a cone of depression, but then the problem is, since they're pumping out even more, it's getting lower and lower and lower year after year. even if you have steady state, so in this diagram that's on the screen right now, let's assume steady state. There's exactly as much water coming in from recharge to the area as there is withdrawals that they're pumping out from the discharge. Even in steady state, there's still going to be a cone of depression. So you shouldn't think that there's only a cone of depression if you have unsteady flow. You still do have this cone of depression for steady flow. But the depth of the cone of depression is dependent on how much water you're taking out. And it makes really sense that, you know, if you're pumping water out of the well, it's got to get back into the well somehow. You know, how is the water moving towards that well? It's coming radially. The flow is coming from all directions. This is just a cross-sectional view, but the water is moving towards the well from this direction. It's moving towards the well from this direction. And why does water move from one place to another? It moves always from high energy towards low energy. You know, water flows downhill. And so you can think of this as the hill. Water flows downhill. Here's the hill. Water is moving towards the well because there is a location of low energy inside of the well. This represents the water surface inside of the well. And so the radius of influence is how far away from the well you are until you don't see any sort of depression. That the drawdown, as it's called, is 0. There's a variety of different like notation systems that are used to like what variable to use for drawdown. And in one of the texts I've used in the past, they give that the variable S. Drawdown being, here's where the water level used to be. See static water table? If there's no pumping, how deep beneath the surface is the water table? So drawdown is how much below the static water table is the water surface when there's pumping. Yeah, it's a funnel shape. Now, the drawdown depends on a lot of different factors. Like this first drawing showed that, here's another great question. I keep thinking of great questions during the wrong time, great exam questions. So if I said draw a cross-section that shows the drawdown for a high flow rate and a low flow rate, what you'd need to do, first of all, is remember it's a cone shape. The drawdown is deepest near the well, and there's some radius of influence. But then high flow rate versus low flow rate, you need to remember that for a high flow rate, you have the most drawdown, and for the low flow rate, the drawdown isn't quite as severe. So that's one trend, is that the shape of the drawdown depends on the flow rate out of the well. Okay, so let's compare a few other shapes. Aquifer material. So what's the difference between gravel and sand? Why is the drawdown different for those two different soils? Like specifically, not it's different because they're different soils. You know, like why is it deeper over here for the sand? Why is there more drawdown for the sand than compared to the gravel? Water moves easier in the gravel, so remember that drawdown is the driving force. That's why water is moving towards the well. The water has to overcome some resistance. Think about the path that it's taking on the way towards the well. It's winding through and it's bumping into obstacles. And so what sort of obstacles, how many collisions does a drop of water face when it's going through fine sand? It's got to wind its way through a really circuitous path. The voids are so small that really a lot of energy is required to overcome that resistance. And so you have a big drawdown because that's what it takes to get the water through that low hydraulic conductivity sand. The K value of sand is very low, meaning that a lot of energy is required to get a high flow rate. By contrast, the gravel, like you guys pointed out, it has a high K value, meaning you don't need very much energy to overcome the collisions as you flow towards the well. The voids are large. You know, if the particles themselves are large, the voids are large also. And so it's easy. The water's flowing through a big channel practically on its way towards the well casing, and so you don't need as much drawdown. The drawdown is the driving force, and you need more driving force when you've got smaller voids. Big voids, small voids. I guess that's to reduce it to its simplest terms, the size of the voids dictates, but it's not just the void size, because remember, some particles actually have an attraction for water. Clay actually has an electrostatic attraction to water because of the negative charged particles. And so it's partly void size, and then it's other factors as well. But K value, you can say that it all does come down to K value, because the K value accounts for that. It accounts for the void size, the attraction of the particles, interaction with the water, and so on. Any comments about this? Questions? What if you have two wells? This is the illustration of you've got well A, and if there wasn't a well B, if it was just well A, this is what the cone of depression would look like, this one. But you've got well B pretty close by, within the radius of influence. And so the drawdown is additive, is the interpretation. Off in the margin of this drawing, what you should say, the take-home message of this drawing is the drawdown is additive. Both wells have their drawdowns lower than they would be if it was just a single well. All right. Here's some terms that I want to identify for you and explain. Fully penetrating means that the well goes all the way down through the aquifer to whatever confining layer is beneath it. So let me show you the opposite of fully penetrating. Okay. This well is now not fully penetrating because I've erased some of if the well casing only goes part of the way down, then this is non-fully penetrating. Fully penetrating means that you are extracting water at the entire depth of the aquifer thickness B. B is the variable that's assigned to tell you how high, what the water height is from the confining layer up to the free surface. All right, the screen depth or screen location, you're just trying to identify, in some cases, for whatever reason, you don't always know where what the drawdown is going to look like, and so you maybe only put in screening, that perforated pipe, for part of the depth. And so it might be that here you've got screening, it's fully penetrated, but then the screening isn't as deep as the aquifer itself. In the equations that we're going to be working with, we assume that the well is fully penetrating and it's screened all the way through the thickness of the aquifer. The situation is a little bit different if that's not true, if it's not fully penetrating or if it's not screened the entire depth. The other thing, well radius. Now, we've already talked about radius of influence. Radius of influence is how far from the center of the well until you get farther and farther away from the well and there's no drawdown anymore. That the static water table is the same as whatever the depth of the actual water height is. The radius of the well, like on the FE exam, there's lots of questions like this. A lot of these well questions. Usually, in hydraulics, we're talking about pipe diameters. That's the common way to talk about things. So it's like, we're always trying to trick you on exams. We'll say, we've got a well that is 1 meter in diameter. Well, the radius is what you need to use in calculations. And so whatever the diameter of the well is, half of that is the well radius. And so in a lot of these questions, we'll throw at you, you'll have to use 2 different radiuses to solve the question, and one of them will be just whatever the radius of the well is. Transmissivity is a term that's sometimes used to identify how much you can extract from a well based on both the depth of the water surface, B, and also the hydraulic conductivity of the soil that it's in. So here's the terms. K value is the hydraulic conductivity, aquifer thickness is B, transmissivity we've just talked about. Piezometric head is how high the water level will rise to. And then what we haven't talked about recently is effective porosity. We did talk about this when we were discussing infiltration rates, but the effective porosity is how much of the soil actually water can flow through. So it takes into account the porosity that isn't connected or rocks that have voids that are all sealed off. Okay, so here's the equation that is used for a confined aquifer. The confined aquifer is a confining layer at the very bottom, and then you can see that there's also a confining layer above it. So it may be that this is water that's between two layers of clay or rocks, but it has some thickness B. H sub W is the height of the water in the well. You can see that this well is screened. It's fully penetrating, so it goes to the bottom of the aquifer, and it's screened through the entire height of the thickness of the aquifer. And then when you get farther away from the center of the well, everything's measured from the center of the well. When you get far away from it, then it reaches its static water height, the initial piezometric surface H. So here's the equation, the well equation for a confined aquifer. You can either use this equation to describe what is the depth of the water above the confining layer, but more usefully, these equations, this equation and one like it for an unconfined aquifer, is used to describe how much water can be extracted from a well for a certain radius and a certain H. Okay, here's a really important asterisk to put next to the slide. 1, when we're talking about 1 and 2, 1 is the location that's closer to the well, and 2 is the location that's farther away from the well. Questions for this are really hard to write. It's like these types of questions are notoriously difficult because you've got a natural log and just like making up what the radii should be and how high the water should be and coming up with a reasonable extraction flow rate. These are hard questions to write, and that doesn't relate at all to 1 versus 2. I'm just helping you understand my pain. So let's do an example here. We've got a confined aquifer. Here's the well equation, and I'd like you to get with the partner and try and find out what flow rate is going to cause the drawdown that is specified there. We have the thickness of the well specified, the hydraulic conductivity is given, and you know the initial water surface. So we want to find out how much is this person pumping out to cause the conditions that are described. I'm going to pause the recording and give you some time to solve that. All right, so we can calculate the transmissivity of the aquifer by multiplying K times B. Get the transmissivity is 132 meters squared per day. So that's a flux if you look at the units. And then from there it's just substituting these values into the equation. And of course the big thing to remember is that location 2 is always whatever's further away from the well. And so H2 is 14.31 meters, H1 13.85 meters. That makes R2 85 meters, R1 40 meters. And the flow rate out of that well is 506 cubic meters per day for the situation that's described. As you were working on that, I added a second part to the question, just because we've got time and can examine that. It asks, if the well diameter is 0.5 meters, then how deep will the water at the well be? And by the way, I have to emphasize something, is that in the confined aquifer example, it's not telling you how deep the water surface is, but it's describing the piezometric surface. And so the water surface, the water is confined by that upper layer of clay. The water itself doesn't go up to this line. That's just where the water would go if a piezometer was put into place here. You know, like if you punctured that upper confining layer and you put in a monitoring well, the water would rise to this surface at the monitoring well. So it's an indication of how much pressure there is inside of the aquifer. That's what this curved line is, you know, in contrast to next time on Thursday, we're going to talk about unconfined aquifers. In an unconfined aquifer, there's a similar drawdown, but the drawdown is actually in the physical shape of the water surface. Here, it's not the water surface that's being drawn down. It's the pressure. Okay, so part 2 of the question is, what if we know the diameter of the well is 0.5 meters? Then, what's the water depth inside of the well? And here you can see that actually in the well, it's not just talking about a pressure. That is the free surface of the water, because once the water gets into the well, it's acting as though it's a piezometer. The water level rises to however much pressure is inside the aquifer at that point. So it's the physical surface of the water. So the key to this question is saying, all right, we've got another radius and another water height. So in the part 2 of this question, we're saying let R1 equal 0.25 meters. But how can that be? We already had an R1 in the previous problem. What do you think is going to be our solution strategy to applying this equation when it comes to identifying what is R1 and what is R2? What do you think, Michelle? Igor? Yeah. It actually doesn't matter. We can pick either one of these other points that have already been described and call it location 2. Because our new location 1 is just, it's going to be the one that's closest to the center line of the well. So R1 is going to be 0.25 meters. H1 is going to be the unknown. And then we're going to have R2 be whichever one. It doesn't matter. We can have it be the one that we've called location 1 before, because this new location 2 is further away from the well. So I did it as, let's call this spot that's 40 meters away, let's call that location 2, and we know that the height of the water there, H2 as we're going to call it now, is 13.85 meters. All right, so the flow rate we already found was 506 cubic meters per day. So now it's just a matter of a little bit of algebra, rearranging the well equation. So we're in the process of rearranging it. We have QW times ln of R2 divided by R1, 2 pi transmissivity H2 minus H1. And we're just rearranging it to try and isolate the H1 variable. H1 is H2 minus QW ln of R2 divided by R1 divided by 2 pi t. So it's going to tell us how deep is the water at the well as a function of how deep is the water 40 meters away from the well. Okay, so the water depth 40 meters from the well was 13.85 meters minus the 506 cubic meters per day, and then ln of 40 meters divided by 0.25 meters. And remember, we were given a well diameter, and the radius is half the well diameter. That's tricky. 2 pi and the transmissivity, 132 meters squared per day. So are the units going to work out the way that we want? We want these units to be in terms of meters, this second term of the equation, and yes it does, because we had cubic meters per second being divided by meters per day, not second. Cubic meters per day divided by meters squared per day. So that is H1 is 10.75 meters. So that's how deep the water is going to be at the well for this well diameter of 0.5 meters. And it's strange, but if you had a different diameter well, that would actually affect how deep the water is at the well. Not by a lot, but a little. Any questions about confined aquifers? Recharge? Okay, so when we get together on Thursday, we're going to talk a little bit more about the exam. We'll do a little bit more subsurface hydrology. And then if you haven't already done the evaluations, we'll have some time on Thursday to open up the tablet cart and do the course evaluations. So I will see you then.